by 1,000. Now it's taking hours. Okay? As a computer scientist, what would you want to do? You want to figure out is, can you speed it up, right? And certainly the ranking does change, but does it change at every time instant? So over here this was better, this still better, now it got worse, right? So was there a point to recompute it, at both of them? Probably not. You compute it once here and maybe you want to compute it once here, right? So those are those change point and critical time point kind of idea. So we'll probably have guest speaker Vishwanath, your advisor. So part of his thesis was to reduce the cost of this problem. Okay. But let's now come back to human reasoning. Okay. For human reasoning, this representation, you have to really keep track and jump around. So a better representation actually is what is called time expanded graph. So let me just briefly introduce what it is. So in time expanded graph, we actually stitch together all these snapshots. Okay. So the way it works is the following. So all the nodes for time t equal to 0, they are listed here. Okay. And we have put a suffix to tell you the time. Okay. The nodes at time 1 are listed here, time 2 are listed here, and so on. So the set of nodes are same as here, just the naming has been changed to show you the time. Okay. But the edges have been changed. Okay. Now notice the edges, they go from one snapshot to the next. Okay. How can we trace where they go? So let's again go back to our ACD. Okay. Notice that AC. So if I start from A at time 0, I reach C at time 1. So A is 0. If I go to C, that's C1. Does that make sense? It basically did the same thing. I started at A at time 0, but I reached to C at time 1. But in this representation, that has been hard-coded. So for humans, it's a little easier to stay correct, right? Make fewer mistakes. And the same thing, if I'm going from C to D, then again you will see the same thing. If I started at C at time 0, I reach D at time 3. Okay. So now the same question, if I wanted to trace, in this one it will be much easier. Okay. So which is the start node in this question? A1. Okay. Everyone, A1. So that's where we are starting. And we want to go to C. So C, if I go down, C2, then I want to go to D, D4, okay. So travel time is 4 minus 1, 3. So for human reasoning, this representation is much nicer, okay. So I'll pause here again, see if there are any questions on what is time expanded graph representation.
T1 because we are studying the snapshot at T1.
In the question I had said start with 1, okay. Yeah. But if you started at 0, then you will start from here, right? And then C and then D, okay? Yeah. In this case, actually, you are ending up at the same time. Whether you start at 0 or 1, you end up at D at the same time, okay? So again, this representation, you will be surprised. It's more than 50 years old. So you may wonder why were people using this 50 years ago? What kinds of problems motivated this? And in fact, there is a very, very nice social application where this representation is used. Okay. It's the public transportation. Okay. When you have your bus schedule and train schedule and airplane schedule, then this is the representation which makes it very easy for you to know which route to take in public transportation. Okay. But with the new road maps where you have temporally detailed data, now these things are becoming relevant even for Google Maps kind of world. Okay. But is everyone comfortable? But this came from operations research. So as a computer scientist, you should look at it and say that is there something computer scientists can add to this representation? So is there a data structure opportunity here? So again, remember how big were our road maps? Okay, 1960, they didn't have much data. Okay. The nodes and graphs operations research people used had 100 nodes if you were lucky. And how many nodes we have in the roadmap of India or US? Tens of millions. Okay, that was a single snapshot. Let's think of this is 10 million. How many of these time points we are looking at? Okay, maybe thousands. Now you got a billion node graph. okay, storage as well as compute time. So as a computer scientist, is that a great data structure, or do you think you have room to make it more compact, maybe? Yeah. So is there any redundant information here across snapshots that we could just keep one copy? What is not changing across? Yeah, go ahead. So let's not even worry about the paths now. I'm just looking at the graph. You're thinking about this as an adjacency list kind of level. But when I'm doing this, is there some information which actually didn't really change from one snapshot to the other, but I was still making copies?
Like T0 to T1
Right. There was no change in edge cost. But if you think about the basic topology, that set of nodes and edges, they didn't change very much. So, but why are we copying them so many times? The only thing that was changing was edge cost, right? So from a computer science perspective, you can actually condense this by having just one copy of your graph nodes and edges. And then what you could do is the edge cost, instead of being a scalar, you could make it a time series. Okay? So if you did that, then the replicating nodes and edges, that will go away. And you will have a huge amount of storage saving. And even in the time series of edge cost, you can start doing some compression because, nighttime, non-rush hour, not a whole lot changes in every place, right? I mean, there are some roads in Delhi and Bombay which are busy even midnight, but many roads are not, right? So you can do lots of compression. So again, this is in operations research. Operations research usually does not think as much about efficiency of storage or algorithm, and computer science can add a lot of value. So there is another representation called time aggregated graph which tries to condense it and so on. All right, so this was, I just wanted to give you a flavor of this is still a very open, rich space, and a lot of computer science creativity can be done, even though the basic static graph and routing has been commercialized. Okay. So with this, we'll wrap up this discussion. If there are any quick questions, let's take those, and then we'll go to the tutorial and exercises. Okay. And by the way, on day 5, when we talk about evacuation, you will see this representation being used, because in case of evacuation, the demands exceed supply so much that the same route has to be used again and again and again. So you have to model the temporal aspect. Yeah. to do even if also, actually Vishwanath is pretty good at that point. You may want to show your implementation to him. Okay. For 50,000 nodes, he will accept that concept. Yeah. So he might be able to tell you a very basic data structure. Even in Typescribe, how you do the data structure. How you maintain open list and closed list makes it useful. If you use the simple linear list, you get slow. If you do heaps, it will be better, but there are certain types of heaps it will be even better. So routing algorithms have been well explored. Okay, so you should be, and Vishnath is pretty familiar with that and very quickly bring you up to date. But the open areas are where you do a way to add some time, or you change the cost metric very drastically. But if you want to do distance travel time, show you some values. So the way you wrote it, maybe make it up, or the pseudocode you use. And asymptotic complexes, they often don't get it. Okay. Okay. And in order to scale up, any software, usually there are, two major tactics. One comes in the form so they all have for 10 years. Not only that, they actually have passenger counters. How many people get on and off the stop, whatever. So they basically are tracking huge amount of identity data. And they want to keep the history of that because most public transportation is government subsidy. And government wants that counters. So they are constantly asking them, either tell me there is a social reason for me to do something or stop. So those data sets are complex. Because this last 40 years, every route, every time, every data sets they will store because that's the way they do it for subsidy. If they want to change the pay, it's a publicly paid for. So they have to go, they need to show all the data to the administrator saying or if they want to add then all the legislature will ask for show me one. I think most major cities, buses are getting the have that kind of data. Roadmaps, the data set has come, it's not traffic, mapping of this is right now, it's all major US cities. They have published 5 years. Yes, I have products.
Because one person Yeah, it can be fragmented and segmented.
This one I wanted to have just a little bit of teaser. Computer scientists are getting a little bored.
In this case, it will be equal to 1.5
This one gets snapped off and this between 3 and 4. This will be two edges. Yeah, two edges.
Morning element is going from residential to outside. But these are two sides of the road. Right? So you will see one side is different. And I have a lot of visualizations of this. You guys I will show you. I can actually tomorrow one of those will come up.
So the final
So I will
session,
pause there and
1:30, the discussion, he said try to get the experts from the space because they work on the scenarios.
So this is a problem which was related to your flight with distributing it.
So in this case, this will be two edges.
So we will discuss it together. So right now,
It is a question, like, right, taking answer. I'm saying it's a two room.
okay.
If this is two edges,
If you put them in different blocks, then you're cutting two edges. Yeah.
yeah, that is the risk.
So
Because look at it from the data perspective also, like they feature in each other's adjacency. So they get snapped off.
no, you just walk around. So this is sort of the blood one, the computational view. So but the preference interestingly, the one algorithm is what everybody uses in GIS and geography. That's the first one. This is what a computer scientist uses. So this is a blend of GIS and computer science. So you can see if it makes sense.
Yes.
And then maybe at that discussion I will invite you to.
After that link which you were trying to
This is a this is what I was trying to see if it makes sense, connects to your application. Okay. So this is saying why why the IS people should talk to computer science people. It's a real actually case.
There is a button.
So there is the buttons here. This time it looks. Okay, this one is push it in.
Actually, the power just
Yeah.
got shaken. It just got shaken.
Shaking. Okay. We just are going to use the whiteboard. So.
Yeah, that is.
Yesterday the staff somehow figured out.
Okay, I call.
May not have connection with this though.
Because everyone has paper copies, so we just want some whiteboard space.
He pressed it here and it immediately obeyed. Yeah, yesterday also we tried.
Oh, there it is. Okay, that was the magic.
I think they put this in the
Oh,
opposite
opposite
direction.
direction,
Because
okay.
these wires are opposite.
I see.
I was trying to do it.
Okay, so now we know.
Reverse gradient. Because the elevation is given, so the reverse.
To see where the bondage happens. Only is going to happen that is where the maximum damage is. Like in this case.
Therefore, yeah, since P becomes the source for the reverse.
P become the quantity where the water will get collected.
got the.
You got a step to say for rank 1 to max, assign a cumulative waterflow of load to the gradient descent. So let's say J has got waterflow 1. So at O the optimal waterflow comes to 1. Now if you go ahead in the loaded one and come to O, you already have M plus about N. 1, 2. So these 2 O's become 4. So 4 plus 1, it will be 5 with it. We have 5. Similarly, add this and
It
add
will
this.
come from here, yeah.
There are 3 to 3. So that you will not get what you do. So you will get this chart faster than this.
And what is the justification? Some of the notes from here, because of this table, they don't get, they
No,
don't
there is
have
no
to
reversal.
visit.
There is no reversal.
So they don't get touched, those notes don't get visited, so therefore you have the
Lesser number
computational
of
advantage.
lesser number of computations you want. Because if you do the reverse, you see the reverse also. Each node reverse gradient descent map you have to use. So you have to work like this, reverse gradient. So from here, you will first do them first here, then do like this, then do like this. Then come back, then do that, then come here. You do this, come back to this, come back to this. In this case, you mix up the gate from here to this. Next,
In this example, we have to deliver so what I have given you are from research papers. But you're right, in this example, but in general, there are other more complicated cases. Yeah, but certainly that's one other thing you can say, can I do it better? But are you comfortable with both of them? You might probably just put under group 3. And you can also write that file that files one other group.
So some of the notes don't get visited at all.
there's no reverse movement. The moment you fix this O, then next thing you go in the upper line. And from there you fix the next one. E का कहीं नहीं, it stops. Because here E is got nothing. You stop here with P. So you take A to F, then you go F, F to P. And you go P to P. After P stops. So there is no reverse movement. Like in this case, it's not a reverse movement. It has to go up this chain, come back, then go here, then come here, then go up there, go there, then come back here, then go like this. Second algorithm is this. It's a very important aspect of GIS. You asked this question. plus 1 of its own. This will be 6. Here this will be 3. From 1 it comes here. So 1 of its own and 1 from top. From 2 it comes from and 1 more 3. So 6 plus 3 is 9 plus 1 10 plus 1 of its own. So we find it over here.
If you have it like very thin slide, you can show at least you will mind speaking a few minutes, then people will.
I actually had got different people. I was planning to get it tomorrow.
But I will invite you.
In fact, I can fill on the board.
Okay, so you can erase and. So hydrologist, that's something.
Yeah.
Arc hydropathy, maybe mix.
The same mentioned by
Okay.
3.
All right, so let's go to this section. Okay, so I hope we all had plenty of time. I see discussions converge much quieter. So let's look at 2 sample answers for the quiz and exercise, and also see if you have any other answers. So for the quiz, you see 2 answers published here. Are there others that people want to add? Okay. For 3, what do you have?
This is a B.
B, okay. All right, any other answers? Okay, so let's start with question 1, and there are 2 answers, B and D. So, all right, so how many voted for B, saying it's not a spatial network? Okay, quite a few. All right, how many voted for D, saying it's not a spatial network? Quite a few, okay. All right, so this was a trick question. So if you are a spatial person, anything that's in physical world has a spatial aspects, right? So internet, traditionally, people didn't think of it as a spatial network, but what you will be surprised to know now, there are databases like IP to location, right? Most IP's addresses have been mapped at, the resolution may not be great. If the IP address is sitting in Eastern Europe and the country doesn't share that information, it will be at country level. But you at least know at that level. If you are in India or in US, you will know it at city or block level, okay? So internet no longer is just cyberspace. It is actually physical space. And for computer security reason, that's a very powerful piece of information. When you get these hacks and attacks, right now, they always trace it back to the country. They can trace it back to a building, okay? And it's very important for both homeland security as well as other kinds of things, okay? So internet today is spatial. In fact, the next internet protocol, IPv6, in the protocol, in the header of your packet, there will be information to have location, okay? Okay, country boundaries, same way. So remember, actually, when we talk about graphs, they are nothing but representing a relationship among some kind of entities. So can you think of any relationships among country boundaries? Neighbor. If I look at neighbor relationship, can I make a graph out of countries? Will that be a spatial graph? Yes, right? So it may not look like network in the beginning, but graphs are powerful models, and that's what this exercise actually showed you, right? Exercise, we started with elevation data. It did not look like graph, did it? Right? But modeling it as graph had some benefit. Okay, so this was a trick question. Basically, lots of things. As long as you have some entities and a relationship, you can make a graph out of it. And if either relationship or the entity has a spatial angle, the graph will have a spatial angle. Okay? All right. Any further discussion on question 1? Okay, good. All right. Question 2. Which of the following are queries on road networks? And the choices we got. Okay, both are D. And so looks like there is a consensus, but you can quickly go through that. I'm asking, which road intersections in this particular town have turn restrictions. So you can again imagine in SQL, right? You can query the graph. Which road segment does this given street address belong to? Okay. So again, as you know, in road maps, for every road segment on each side, they have starting and ending street address. That's the typical representation. So you can easily go through that and search. Shortest path, we have all seen that. Okay, good. All right, let's go to question 3. Which of the following is a disk-based data structure? And let's see the choices. So we had everything A, B, and C. Okay. All right. So let's quickly go over that. Right. So the way we at least discussed adjacency matrix was discussed under memory, and that's where they are typically used. Okay. So most of the linear algebra software has not been adapted for disk. Okay. In fact, vast majority of software, when they start, they all assume things are in main memory. Okay. And occasionally there has been big battles. Tomorrow you will hear about one of them. So all the statistical software till 90s, they used to assume data can be loaded in main memory, right? SAS, SPSS, and so on. But then relational databases were growing in parallel, and they were dealing with data sets which did not fit in main memory, right? This problem has resurfaced with big data now. Okay? And so there was a big battle. The statistics companies were not ready to deal with that. So that's how data mining was born. The first purpose of data mining was to scale up common statistical algorithms to work on out-of-core data. Okay, and initially SAS and all ignored it. Statistics called data mining black magic and whatnot. But they came around, and today SAS packages, they would deal with out-of-core data. Okay, so adjacency matrix was primarily main memory. Stack, if you know, we never brought it up. Stack again is used in main memory, right? You have seen a lot of use of stacks for do recursion and things like that. The one we discussed primarily was this denormalized node tables. So when you are thinking about tabular structures, they are for databases, and they often are. Okay. All right. Question 3. Further discussion on this one. Okay. All right. Let's go to question 4. How many edges are cut if a disk page contains node 1, 4, and 5? And let's see the choices. Okay. Consensus is C, which is 3. All right, and you can kind of see the edges which will be cut will be between 3 and 4. There are 2 edges, and between 1 and 2 there is 1 edge, right? So everyone comfortable with that one? Okay. All right, let's go to question 5. And it's saying which node is not expanded by Dijkstra's algorithm in computing shortest path from 1 to 5? And all voted for D, which is 6. I do know there was another choice in the back. Do you guys want to publish as well? 4. Okay, so that's node 4.
4 is not part of the answer.
It's not part of the answer, but sometimes question papers can have mistakes, so should still entertain.
Then 4 is the answer. carrying on that.
Okay, so let's at least trace through Dijkstra and see what would happen. Okay, so we are going to start from node 1. And the first, the neighbors 2 and 3 will be on the open list, right? And you are going to pick up 2 because it's closer to 1, right? So 1, then we go to 2. And now the open list will have 3 as well as 5, right? And which one will we pick next? 3. It's closer to 1. So we have now expanded 1, 2, and 3. And now 4 and 5 are on the open list. Which one will we pick? 5, right? It's closer to 1. So 4 is not expanded because after 5, 6 will be in the open list, and you can now ask between 4 and 6, which one will we pick? That 6 is closer, right? So 4 will never be expanded. So we apologize for the typo. Okay. So the answer should be node 4 is not expanded. Yeah. Okay. Are we okay on this? Which one is not expanded? 6. Okay, 6 is also not expanded. So D is also correct. So we are sort of in both answers are correct. Okay. Because once you reach expand 5, you are done. All right. Both answers are fine. Any further question on this? Okay, let's continue on question number 6. Which is the shortest path from node 1 to 5? And we both voted for A. So just look at that. Yeah, so you can just calculate the cost, right? So A is going through 1, 2, 3, 5. Your total cost is 4. And then it's very hard to beat, right? Everything else looks bigger. Yeah. Okay, good. So everyone set with question 6. Let's go to 7. Which one is false? And we have choices. Okay, A and B. How many vote for A? Here. Few. How many vote for B? Lot more. Okay, let's look at that. So A said hierarchical routing algorithm works with graphs that do not fit in main memory. And as I was telling you, that is the history. That's where it came from. So that is indeed true. Although nowadays that's not the common use case for that because memories are bigger. Okay, so A is true. Okay, let's go to B. Hierarchical routing algorithm is an approximation algorithm. So how many of us don't know the meaning of approximation algorithm? Few of us. Okay, good. So this is a term from computer science or theory of computer science. So it first is in order to understand that you have to understand that problems are categorized in computer science by their complexity, particularly worst case complexity. And there is a family where the worst case complexity informally is exponential in the size of the problem, right? These are called the NP, NP complete, NP hard family. Okay. And once you are in that space, people usually don't try to design algorithms to find optimal solution because it will take enormous amount of time even for a small problem. So then the expectation is changed. Then you say, okay, if I want fast algorithm and I cannot guarantee optimal, can I guarantee something else? Can I be close to optimal? Can I be within a factor of 2 of optimal or factor of 5 of optimal or something? Okay? And those algorithms are called approximation algorithms. Okay? The reason this question is here is the following. Actually, there is a competitor to hierarchical routing algorithm called contraction hierarchies, which came from theory of computation, and that is an approximation algorithm. Okay, but what we gave you is not. It gives you optimal route. Okay, so hierarchical algorithm, the one I gave you, is an exact algorithm. But there is a competitor called contraction hierarchy, which you will come across, which is an approximation algorithm. Okay, so B is false. Okay, all right. So I think that was the ambiguity. Rest we all agree is true. Good. Any other thoughts, questions on the quiz? Yes.
Make the nodes on basis of the Euclidean distances.
Right.
How do we get the exact answer?
Okay, very good question. So this question actually pertains not to hierarchical routing algorithm, but it pertains to A star. So how many of us remember the reasoning to say A star finds optimal route even though it is using an underestimate of Euclidean distance as the heuristic? What is the argument that it gives you an optimal solution? Anyone remembers this?
Suboptimal part still holds for H star.
Okay.
Head for Dijkstra.
Right.
Only we are reaching the expansion part.
More goal it is more localized expansion because
Right,
the
right.
direction there is more directional vis-a-vis to start to widen.
It is, but when you expand the goal node, at that time, have we actually discovered the optimal path, or could we get a better path later on? That's basically your argument, right? And so, does the use of Euclidean distance affect this Dijkstra property, right? That's your question. And so you can look at the proof. Your AI books will give you the proof, but I think it's centered around the negative edge cost. Okay, it's basically once you expand that, then what you can think about is the following. Once you have expanded the goal node, you have found the path, and after that, any path that you enumerate, its cost will be higher, because the newer edges you're adding are all going to be non-zero positive cost. Okay, so it's based on the negative cost argument. It's pretty much the same. Okay, so once you expand the node, you have an exact cost. This is what you have to remember. Okay. Once you expand a node, you have exact cost for the path from source to that node. Okay, but the ones which were on the open list, which were not expanded, for them you have approximate cost. Okay, but once you expand it, you have exact cost. Okay? All right. Any other thought, question on this? Okay, so let's go to the other sheet, exercise sheet, and actually to give you the background of this, let me maybe first invite one of the participants to actually tell you it's modeling a real problem, which is also relevant to India, and there was a recent case where this kind of a modeling was important. So do you want to maybe come over and talk about it a little bit? This way.
Few years back, as all of us were aware, Kashmir Valley was flooded. It was first time in its history from independence that a valley was flooded, and the water column at the base, that is Srinagar and around, went up by almost 40 meters. 40 meters, that is vertical. So buildings till second floor were submerged. Now, what we were modeling initially for rescue plans was, first you start with what is called the watershed, which is somewhat mentioned in this sheet as the first part, because watershed gives out the flow of water and the direction and to where its terminal location would be. And wherever the terminal location would be, classically we call it pondage, where the water starts getting collected. So what happened in case of Srinagar was, since Srinagar has got Dal Lake, that's the lowest point in that sector, and you got mountains around it, that is Dachigam Hills, you got Gund, you got Kangan, all these are hills around Srinagar. How many of you been to Srinagar? So there's a Dal Lake and you see mountains all around. So the natural watershed, there is anything coming on these mountains will naturally end up into the valley. And that valley at that time only had one outlet, that was Jhelum. So from inlet to outlet, the proportion was so high that Jhelum also started bloating. So rather than pushing the water out, Jhelum also added to the flood. So for being part of the search and rescue group, we initially modeled the heights using DEM models and worked out the watersheds. So we realized that about 6 to 7 channels which will flow into Srinagar. And then computing using GIS as to how much volume per hour. There's a dam break model in GIS which we used, what will be the flooding per hour. And seeing the area of Srinagar, we worked out how much would be the vertical rise. So that gave us the amount of time we have to carry out rescue. And submergence also gave us the option to see as to in how many hours which all roads will get submerged and so what are the alternate routes. So as you have this maximum route planning at T+5, some roads were not available. At T+12, some roads were further not available. So that is how our rescue was planned. Actually, it was my fault. I was supposed to get a small PowerPoint for this. Tomorrow, day after, anybody interested, carry a copy. You can have a look how the modeling was done. And the other aspect which comes into play is heuristic data. That is, we picked up the data from the J&K state as to which months you have maximum rainfall and which months you have maximum pondage. So that coupled with all this information, we were able to come to a rescue saving of almost cutting down from 72 to 2 hours to 14 hours based on these calculations. That's all.
So this kind of modeling is often done in hydrology, okay? But it's also an interesting story for computer science, because you can guess, which algorithm do you think is used by hydrologists? We gave you the algorithm 1 or algorithm 2. Which one do you think a hydrologist or a civil engineer will use? Which one do computer scientists prefer? 2, right? Because its complexity is lower, and it actually came out from Lars Arge's group in Duke University with a project to do exactly this. But if you go to civil engineering, they use number 1. Okay. They use kind of number 1. It's a more, even actually it's slower than that. They use a transitive closure algorithm. It's almost cubic algorithm. So when, if you look at the typical software which will do this simulation, it takes much longer. But whereas if you kind of start bringing in your algorithmic knowledge, you can speed it up. Okay. But as I said, it's a real problem. It's done for many reasons. If you have heavy rainfall, you just heard, people try to simulate if there will be downstream flooding. And it's also done for snow melting. So a lot of areas, the winter is long and snow doesn't melt, it accumulates. So in spring, there is a similar modeling saying how much snow has accumulated and how much is the water content. They go take samples, and if it melts, then where will the water go? And it has 2 different aspects. In dry areas like California, they worry whether they would have enough water for their agriculture and drinking. But areas like Midwest, they worry that it will flood. Okay. So let's look at the answers. For the first part, we were saying which algorithm it has lower computational cost. And looks like we both answers said algorithm 2, right? So everyone comfortable with that? Okay. And the second part was to justify your answer. In this case, asymptotic cost analysis, worst case cost analysis, is a simple way to justify. The first algorithm, as you can see the reasoning, depth first search, we said is linear cost, and you run it for each node, its total is quadratic, whereas the second algorithm will be n log n, right? But this is a true life story where computer science involvement in modeling terrains made a big difference. And there are many such opportunities, okay? But I will also tell you a flip of this so that we find a balance. It's not just knowledge only goes one way, it also goes the other way. So there is another task in maps called line generalization. So if you have a long river and so on, if you zoom out, you cannot maintain the exact geometry. It gets too close. So they simplify the line. And in geography domain, there is a very well-known algorithm. Okay, maybe the GIS folks, you can tell me what's the line simplification algorithm that every geographer will use or every software will use. Anyone name that algorithm? Okay, Douglas-Pucker algorithm. Anyone heard of this? All right. But anyway, there is a simple algorithm which is designed by geographers. It has been used for a long time, and its asymptotic complexity is n square. Okay, just to use the same term. But when you look at it, then computer scientists, they say, well, we can reduce the complexity, and they did design a n log n algorithm using convex hulls. Okay, so asymptotically, the new algorithm looks more promising than the old one. However, almost all implementations, Douglas-Pucker still beats the n log n algorithm. Can anyone guess why is that? So this is a lesson for computer scientists that, this asymptotic complexity analysis is a part of the story, but sometimes it helps you, sometimes it doesn't. Any guess why the n log n algorithm does not beat n square algorithm? Okay, it's the constants. Okay, it's the constants that when you are maintaining convex hull and all, you have to actually do a lot of work. Asymptotically doesn't look very sharp, but for average data sets, it does not pan out. Okay, so all right. So this was most of the discussion today. Any quick questions on the quiz or on the material? We'll do that. Okay. Right. Right. Okay, so maybe let's take it one to one. Okay, we'll do that. And just any announcements for tomorrow. Tomorrow we are going to another topic, spatial data mining. So it will be a little bit of statistics and data mining. And I know many of you are interested in that topic, generally machine learning data mining. So please take a look at the reading. There is one survey paper. So take a look at that. It will probably trigger some thought. But if you have taken data mining machine learning course, then you would be essentially seeing that the techniques when you apply to spatial data, what are the challenges, and then how those have been adjusted for spatial data. Okay. Any other organizational announcements that we need to do?
I think it's not been boxed, but there is an announcement about tomorrow afternoon. So take a look at this. You're most welcome to join. Since this topic, spatial big data,